Okay, let's review the linear transformation. There's mainly two problems related to linear transformation. The first is determine if a transformation is linear or not. To determine if a transformation is linear or not, we use the definition of linear transformation. The definition of linear transformation is defined if a transformation is a linear transformation if it satisfies two conditions. The first is Tu plus V equals Tu plus Tv. The second condition is T lambda U equals lambda Tu. For U, V belongs to Rn and lambda belongs to R, that is for any real numbers. So if we want to determine a transformation is linear or not, we just need to check these two conditions. The second problem is related to the standard matrix of linear transformation T. To find the standard matrix of the linear transformation, there's a theorem. If the transformation T is linear, then there exists a matrix A such that Tx equals Ax for all A, and A can be expressed as Te1, Te2, Ten. That means the column vectors of A are all transformations of a standard basis. Okay, let's use these two material to do some examples. The first example is determine the transformation T is linear or not. The T is defined as Txy equals x negative y. That means reflecting the vector by the x-axis. We use those two conditions to determine if T is linear or not. The solution is let U equals x1, y1, and V equals x2, y2. Then we check these two conditions. The first is Tu plus V, that is Tx1, y1 plus x2, y2. First, we add them together, then take the transformation. So that is Tx1 plus x2, y1 plus y2. The linear transformation just changes the sign of the second coordinate. So that is x1 plus x2, negative y1 plus y2. That's the transformation for addition. And the addition for transformation, Tu plus Tv, that is t x1 y1 plus t x2 y2. T x1 y1, that is x1 negative y1. T x2 y2, that is x2 negative y2. Add them together, that is x1 plus x2, that is negative y1 plus y2. This actually the same as tu plus v. So the first condition is satisfied. The second condition, t lambda u, that is t lambda x1 lambda y1. Change the sign of second coordinate, that is negative lambda y1. We take the lambda outside, that is x1 negative y1, that is lambda tu. So the second condition is also satisfied. By these two conditions, we got that t is linear. Let's just check these two conditions. And now we look for some examples of how to find the standard matrix. By the theorem that if we want to find the standard matrix, we focus on the transformation of standard basis. First, find A of T. The T is defined as x1, x2 equals 2x1 minus x2, x1 plus x2. We focus on E1 and E2. So T E1, by the definition, T1 is T1, 0. That means x1 equals 1, x2 equals 0. So T1, 0, that is 2 and 1. Te2, that is T0, 1. That is x1 equals 0 and x2 equals 1. So that is negative 1 and 1. So the matrix is Te1, Te2. That is 2, 1, negative 1, and 1. This is a little bit easy to find the standard matrix. Let's see the rotation. Find A of T. T is defined as rotate vectors by angle theta counterclockwise. Now let's draw the graph of this linear transformation. First, this E1 is changed to this vector. This is theta, and this vector should have new coordinate x and y. How to find x and y? Now, by the definition of the trigonometric ratios, we have x equals x, y. The x coordinate the t e1. The x coordinate of t e1, that is the length times cosine theta. So that is the length is 1, so that is cosine theta. And the length times sine theta is a y coordinate, so that is sine theta. What about TE2? The E2 is changed to this, this is E2. Not that. So here is the theta. Here is the theta. So y, the y coordinate, the length of y is because this line is adjacent of theta by the definition of cosine theta. So y coordinate is cosine theta. But what about the x coordinate? X coordinate, if we choose this angle by the definition of trigonometric ratio, maybe we call this the theta of the theta, then the x coordinate should be cosine theta theta, and that is cosine pi over 2 plus theta. But the cosine pi over 2 plus theta is negative sine theta. So the x coordinate is negative sine theta. So the standard matrix is cosine theta, sine theta, negative sine theta, and cosine theta. That's the standard matrix for rotation. There's even more difficult example. Find a over t. The t is defined as reflecting by the line y equals x. This may not be too hard. Then use the graph y equals x. So this point change to this point, and the E1 change to the E2 because reflection by y equals x. That is just interchange the y-axis and the x-axis. So TE1 equals E2. So E2 as T10. Interchange the x and y coordinate, that is 0, 1, and TE2, that is T01, that is 1, 0. So the matrix, that is 0, 1, and 1, 0. This is not too hard. But if there's reflecting by other line, for example, find a o t. T is defined by reflecting by reflecting by the line. If the line is not y equals x, but y equals 2x, then how to find the TE1 and TE2? There's some trick for this type of transformation. This y equals 2x. So any point on the line does not change by the transformation. Suppose, for example, we use one point that is this point 1, 2. 1, 2 does not change. So that is T1, 2 does not change because this point is on the line. But how to find another one? There's TE1 and TE2, so we need two equations. We use the normal line of this line, of the original line, and crossing the origin. So this line is y equals -1/2 x by the relation of perpendicular lines. So any line on any point on this line change the signs of their coordinates. For example, there's -2 and 1 change to 2 and -1. It's symmetry with the origin. So after reflecting, the -2, 1 change to 2, -1. So that's 2t, 2, -2, 1, and change to 2, -1. There's two methods to find TE1 and TE2. The first one is use the definition of linear transformation. Because T1, 2, that is TE1 plus 2E2. Because E1 is 1, 0 and E2 is 0, 1. By the definition of the linear transformation, it's TE1 plus 2 TE2 equals 1, 2. And T -2, 1 equals T -2 E1 plus E2. That is -2 TE1 plus TE2. That equals 2, -1. So we got two equations. And if we view TE1 and TE2 as unknown variable, then we can solve this linear system by the Gaussian elimination. If we call this the first equation, this is the second equation. First, we times the second equation by 2. Then we have -4 TE1 plus 2 TE2. That's the third one. And use the first equation minus the third equation. We got 5 TE1. 5 TE1. Oh, this equals 4, -2. 5 TE1 equals 1, 2 minus 4, 1, 2 minus 4, -2. That is -3 and 4. So we got TE1, that is -3 over 5 and 4 over 5. This TE1, and we insert this result to the first equation. So TE1 plus 2TE2, that is negative 3 over 5 and 4 over 5 minus 2TE2, that is 1, 2. So 2TE2, that is negative 3 over 5 and 4 over 5 minus 1, 2. Minus 1, 2. TE1. Okay. That is negative. It's negative. Negative 8 over 5. And that's negative. Why is negative? That's plus. That's plus. Sorry. So this is plus. This is negative. So that is 8 over 5 and 6 over 5. That's 2. This one minus this one. Yeah. So we got TE2, that is 4 over 5 and 3 over 5. We divide both sides by 2. 3 over 5. Then we got TE1 and TE2. So A equals TE1, TE2. That is TE1, that is negative 3 over 5, 4 over 5. That is 4 over 5 and 3 over 5. That's the standard matrix. The first method is use the definition of linear transformation. The second method is use the inverse matrix. Use the inverse matrix because Tx equals Ax. So T 1, 2, that is A 1, 2 equals 1, 2, and T negative 2, 1 equals 2, negative 1 equals A negative 2, 1. So we use these two equations. That is A A 1, 2 equals 1, 2, and A negative 2, 1 equals 2, negative 1. So that is A equals 1, 2, 2, negative 1, and 1, negative 2, 2, 1. It's inverse. Use the matrix equation. Okay, the first equation does not change, and we find the inverse matrix of the second one. The inverse of 1, 1, negative 2, 2, 1, that is, use the inverse matrix of order 2. The determinant is 1 plus 4. That's 1. so that's 1/5, and that's 1, 2, -2, 1. That is 1, 2, 2, -1, 1/5, -2/5, 2/5, and 1/5. That is -3/5. 1 times 1/5, 2 times -2/5, and that is 2/5 plus 2/5, that is 4/5. And here is 4/5 and 3/5. This method we use the inverse matrix to find the standard matrix. Actually, the most difficult part for this type of problem is how to find the 2 points, because we cannot use the E1 and E2 directly. So first we find the point on the line does not change, and the point on its normal lines change the signs of its coordinates. Okay, that's the material of linear transformation.